Okay, still in week 2.5. This should be Organic25BBlake, and I'm on page, I just finished with carbene on page 61, 2.15, so we're going to go on to 2.16 on the next page. However, first I have to show you this table, and again, I don't think you really need to memorize everything in the table. As you go through, read it, look at it, make sure you understand it. But you need to understand that nitrogen needs 5 electrons. So you could either have 2 bonds and 2 lone pairs. That'd give you, well, 6. So these are all going to be formal charge -1. You could have 3 bonds and 1 lone pair like you have in ammonia. So these are all no formal charge. And you could have 4 bonds and no lone pairs, which gives you 1, 2, 3, 4, obviously not the 5th one. So you short by an electron, and those all have a positive formal charge. So get to 5. Whoops, this didn't do what I wanted. So on the next one, 2.16, they have a nitrogen with no formal charge, so you should get to 5. 1, 2 for the lone pair, 3, 4, 5. No formal charge on B, so it should have 5. So you got a lone pair and 3, 4, 5. On C, also for the nitrogen, no charge, no formal charge. So I have to have a lone pair, 1, 2, 3, 4, 5 in these bonds. On this one, I must have a lone charge that I don't have up there. Yep. Okay. This is the last example we talked about. I have 4 bonds. 1, 2, 3, 4. I'm short an electron, so I got a positive formal charge. Let's put it right here. All right. Going on. E shows a formal charge, apparently. Yep. So I have to have extra electrons. If I have a lone pair, that's 1, 2, 3, 4, 5, 6. It's 1 too many, so it's negative. F shows no charge, so I must have 5. We do that by putting a lone pair, 1, 2, 3, 4, 5. G, we're showing a formal charge of +1. So it must be 4 bonds and short 1. 1, 2, 3, 4. I don't have my 5th electron, so that's positive. H, showing one of my nitrogen is short a charge. So there's no lone pairs on G. For H, I have 1, 2, 3, 4, and I'm short an electron here, so that's positive. Up here, I have 1, 2, 3, 4, 5 bonds. 2 to the hydrogen, 1 here, and a lone pair. So no formal charge on that one, but I do need the lone pair. 2.17. Each of the following compounds contains both oxygen and nitrogen. So now we're combining both tables, but just as long as you remember oxygen needs to end up with 6 valence electrons or have a charge, and nitrogen needs to end up with 5 valence electrons or have a charge, you should be fine. This isn't hard, it just takes some practice. Page 63, 2.717A. We've got a formal charge on that oxygen and a nitrogen. So oxygen has 1, 2, 3, 4, 5, and I'm still short 1, so that's positive, so I need 1 lone pair here. If I put 1 lone pair on the nitrogen, I've got 1, 2, 3, 4, 5. B. OCN, okay? So my carbon has 1, 2, 3, 4 bonds. My oxygen has, if I put 2 lone pairs in, 1, 2, 3, 4, 5, 6, it's neutral. My nitrogen has a negative formal charge. So if I have 2 lone pairs, I have 1, 2, 3, 4, 5, and a 6th extra one gives me a negative charge. So I need 2 lone pairs to make this happen. For letter C, I have a positive formal charge on nitrogen. So oxygen is 1, 2, 3, 4, 5, 6 apiece. 1, 2, 3, 4, 5, 6. Nitrogen has 4 bonds. I don't have my 5th electron, valence electron, so it's got a positive formal charge. Probably D next. D. I don't know where I'm at. 2.17 D. Okay. All right, I didn't do this one already. Okay, so I need 6 charges on my oxygen. I have no formal charge here, so that works out. 1, 2, 3, 4, 5, 6. I have a negative formal charge here, so I should have an extra one. 1, 2, 3, 4, 5, 6, and there's a 7th one. And this should be short by 1 charge, so it has a formal charge of +1. So we got 1, 2, 3, 4 shared pairs, or 4 electrons that nitrogen has that's shared in the bonds. And I don't have the 5th one, so it's got a +1 charge. On the next one, I'm showing no charges on anything for E. So nitrogen must have 5. 1, 2, 3, 4, 5, and oxygen must have 6. 1, 2, 3, 4, 5, 6. So I need 2 lone pairs on oxygen, 1 lone pair on nitrogen to make that work. F. OCN again, but this time in a different configuration. I have no formal charge on nitrogen, so if I put a lone pair there, I have 1, 2, 3, 4, 5, that's okay. This carbon has 1, 2, 3, 4, it's all right. This oxygen has 1, 2, 3, 4, 5, 6, and a 7th one. It must be negative. In order for this to be negative, you have to have 3 lone pairs. 2.18, identify the number of lone pairs in each of the following compounds. Okay, so if you draw A like so, and you have a formal charge, that means you have 5 electrons on this carbon. If I put a lone pair there, I have 1, 2, 3, 4, 5, and that's what happens. 1 lone pair. Number 2, I have the same chemical, but without the lone pair. I take that lone pair away, I have 1, 2, 3, and that's a positive for a formal charge. So I have 0 lone pairs there that are extra. Well, just 0 lone pairs. C. I'm showing a negative formal charge out there at the end. And I've got a carbon out here and it's triple bonded. So I have to have 1 lone pair here to have the 1, 2, 3, 4, 5. That's 1 more than carbon normally has, which gives me that -1 formal charge. So I have 1 lone pair to make this work. D. You have a negative formal charge here on this carbon, which means you have to have 5 electrons, and the other ones don't have a charge, which means they must have 6. In order to get 6 here, you have to have 1, 2, 3, 4, 5, 6. That's 2 lone pairs. This oxygen is the same. You have to have 5 electrons here. In order to make that work, I have to have a hydrogen bond here that's not shown. That could be the tricky part for you, perhaps. And then I have lone pair 1, 2, 3, 4, 5 is 1 more than 6, so it's a negative charge for a formal charge. Okay, and then they have the question about amino acids. Amino acids. They're biological compounds where the R group can vary. We're going to talk about amino acids in number 25. We're not going to get there, but they're connected together to make proteins. Sometimes people worry about genetically modified foods or something like that. You really don't have to worry about that, because when you eat anything, That's made of cells. That's what you should basically eat, stuff that's made out of cells, not things that aren't made from cells. You've got proteins in them. So if you've got some genetically modified, I don't know, you've got Roundup Ready soybeans and it goes in your tofu, I guess, if you like tofu. You don't have to worry about that because whatever gene is in there that makes a protein, when you digest that food, all those proteins are going to get chopped up into individual amino acids, and you're going to make your proteins out of all those amino acids. So it doesn't matter what the coating was on it. It's all going to get broken down into the amino acids. You're going to assemble your own out of the 24 or 26 or however many amino acids we have. Forget how many we have. All right, well anyway, we show a formal charge of negative on an oxygen, so I need 7 instead of 6. Positive on the nitrogen, so I need 4 instead of 5. So on this NH3 group on the end here, I have 2, 3, 4. It's already positive 1 formal charge. On the oxygen, if I put 3 lone pairs in, I have my 7th one here, which is 1 more than 6, so there's my negative charge. And if I put 2 lone pairs here, I have 1, 2, 3, 4, 5, 6. And then my number of lone pairs is 5 lone pairs. By the way, I had 5 lone pairs back on the previous example in 2.18D if I didn't count them. 1, 2, 3, 4, 5. Where I'm going to end up with this for Monday and Tuesday is wedges and dashes. The book talks about calculate 2 times. One's on page 3 and one's back on page like 283. I learned these as calculate structures, and remember I do them a little differently. I don't know if I told both groups there this one, but if you look at, okay, anyway, this is acyclic, so you have this carbon chain in the plane of the board, and this one coming towards you, and this one is supposed to be going away from you. If it's cyclic, again, you'd have these carbon atoms in the board, this one coming towards you, this one going away from you. Now the way I learned to draw these is, and I'll draw them, starting at the carbon, you start with the bigger line, dashed line, and you go to the smaller ones like it's railroad track ties receding off into the distance. And to me that makes much more sense as the way they should be drawn. Why he drew them this way, I don't know. He draws them the other way. If you have a bicyclic compound, and hopefully we'll get to naming these at the end of the year, you have a ring and then another loop off that ring. This one shows that ring coming towards you and a bromine coming towards you and something else going away. This is probably a hydrogen on here. Again, I would draw it this way. But that doesn't make any sense to have hydrogen on there. Why would you draw a hydrogen on there when you didn't draw any of the others? I don't know. I think that's just an editing problem. There's something supposed to go here, but I don't know what it is. Okay. And then I'm asking you, okay, and there's nobody here. The Fisher projection, you could do those calculate dash and wedge designs or patterns off of here. Haworth projection is only used for cyclic compounds. This shows one edge towards you, another edge away. And bicyclic compounds, if we get that far, we'll do some of these. This would, ME should be a methyl group off that oxygen for whatever reason you put it in there that way, but you can do it that way also. Okay, I'll have to make more video to continue from here. That'll happen probably Wednesday.